Okay, so let's see. We'll go back to this example. I mentioned you want to be able to eliminate stuff that's not important. So let's actually walk through just a quick example of what it looks like to decide something's not important from a resistance perspective. So we're taking our material that we had, material A and B, and now we're giving some actual values to the materials and dimensions and stuff. So let's hold our hot side temperature at 300, our cold side temperature at 100. This is sort of a cryogenic application where we're trying to cool something way down. And we've got two different materials, same dimensions, but different thermal conductivities by an order of magnitude. We have a contact resistance, and then we have convection on both sides with different orders of magnitude. So let's think a little bit about how to organize this. And what you're going to want to do is draw a resistance network. So let's start. So this problem, we go left to right, but just to fit it in, I'm going to go top to bottom on my resistance network. So let's start by drawing a resistance network. So first thing, up at the top, you have a node, and that node corresponds to a temperature, right? A position at which you want to know the temperature. So at that node, that first node is going to be what? T, this is T, it's hard to see, T infinity H. That's this guy over here. All right, so that's the temperature we know. We're given that temperature. And then what? We have convection between that temperature and the surface at material A. So we're going to draw resistance between that temperature and surface A. So we'll call this T surface for material A. And this is going to be a resistance. We'll label this R convection on the hot side. And we could actually go through and calculate its value, right? We know that the resistance for convection is 1 over h bar A. So 1 over h bar, what's the surface area here? Let's see. I guess we weren't given it, but we could assume maybe 1 meter squared for this just to make it easy. So let's assume that the surface area is 1 meter squared. So then we end up calculating this, and it should be, let's see if it hopefully matches my notes, but it's 0.1 Kelvin per watt. All right, so we have an order of magnitude for this. And we can keep moving on. What's the next resistance? Well, in series with this, we have heat flowing this way. So we have our convection. Now we have this node. We have this now conduction resistance. And let's model that. So that would be TSA, another resistance to the next interface. Let's call this resistance of the plane wall in material A. And it's going to some temperature. We could call this like T, maybe AB, right? It's the interface between A and B. And we can calculate the conduction resistance. That's thickness, which is what? L. Right? Thickness over K times A. So it's thickness over Ka, which should be, let's see, it should be 0.01 Kelvin per watt. And we just keep going, right? So do the same thing for T surface B. Let's call this R plane wall B. And that's going to be, oh, sorry. Yep, getting ahead of myself. Right, we have a contact resistance. Okay, contact resistance. Let's put that in there. That's going to be RC. That would be what? 0.001 Kelvin per watt, right? That's the specific resistance divided by the area, 0.001. And now we have, let's see. So my temperature labels are going to be sort of a little bit unhelpful here. Let's call this TAB left and then TAB right, okay? Now we have another resistance. This is R plane wall B. This is 0.1 Kelvin per watt. We have convection on the B side, which is R convection, let's see, to the cold. So that ends up being 0.01 Kelvin per watt. And then out here we are at T infinity C. All right? So if I ask you to draw a resistance network, this is what I'm asking you to do. We want to label where the heat flow is going. So Q dot is going in this direction. So you should have heat flows labeled, any heat flows at any node labeled. You should have the correct topology, right? Every single resistance here is in series. So there's no way that heat can kind of flow in two paths. It's all going in series all the way across. You have every resistance labeled and all the relevant temperatures labeled. Right? So I would get -1 because I didn't label at this point here. This is TSB, right? So this is the point of this is not to be like pedantic, but it is to just give you all the give you labels and schematic for everything you're going to do. All right. So what's the point of this aside from just showing you the approach? Well, the point is to decide what's important. So if I look at this, I can kind of immediately get a sense of where I need to be focusing my modeling attention, right? This is just your first pass at the problem. Maybe you have to do something more detailed. You have to build a 2D model or something like that. All right, so I would go into this and I would say, all right, I know immediately that contact resistance is not very important. And why is it not important? Well, because it doesn't actually affect the delta T in the system, right? Everything else is at least an order of magnitude greater than that in terms of the thermal resistance. So I know right away I can just basically throw away this contact resistance. It's not important. Now, depending on how much I care about being very precise, or maybe I'm really building a model of one side or the other, then you have to make some decisions. But you could also easily argue that the convection here is not important on the cold side. You could argue that the plane wall on the A side is not important. Right? Those are relatively small contributions compared to the bigger things, which are the convection on the hot side and the B side plane wall resistance. Right? So those would be the areas that you would then say, all right, let's go spend some time on this. Right? So the other thing that you can do here is you could sketch out the temperature profile. So let me get the right color. So we can sketch out the temperature profile. So let's do that again. So we have temperature as a function of position x. And we can make the sketch corresponding to now what we know about these plane wall, or what we know about the magnitude of these resistances. And the temperature drop across each resistance, of course, then corresponds to the value that we have here. So let's say we start off at TH, and we end up over here at TC. So my job is to then come up with a relatively accurate sketch of what I think the temperature profile is going to look like. All right, I know, first of all, that my convection resistance is really pretty large. So my temperature drop on the convection side has to be pretty large. So I'd start off at TH, and I'm going to go out of the domain, but we'll see. So the temperature profile would kind of look like this, coming up against the wall. Then I have a plane wall resistance, which should be just a straight line, and that's a really small value compared to the rest of the contribution. So let's see here, coming down. So my next temperature is going to be something, just a really small decrease in temperature. That's a straight line. Then I have basically a negligible contact resistance, so maybe there's just a tiny little drop in temperature. Then on the B side, let's see, I've got a big resistance, another 0.1. So again, I'm going to have a big temperature drop here. And then on the cold side, a relatively small convective loss. So that's going to look something like this. Right? So we've now just come up with a pretty rough but pretty accurate temperature sketch, just without really doing much beyond back of the envelope calculations. So with this knowledge, you can then go in and be much more detailed in the place where you want, where is important for what you're doing. Okay.